My name is Schmidt and I'm a graduate of the IMFSE and a graduate fire engineer at WSP Australia. I will be talking about my research on the burning of engineered timber. In an experimental study, I looked into the effect of char falloff on cross-laminated timber. Timber has many advantages and can help us to find our way towards more sustainable buildings. The way that we use timber in buildings is undergoing a fundamental change. But using timber in modern and especially high-rise buildings affects the challenges and risks that we have to face. Therefore, we must understand exactly how timber reacts in a fire. To study the impact of char falloff, I conducted a series of experiments with CLT columns that were loaded mechanically. The thermal and mechanical degradation of timber are linked, which increases the complexity of the structural analysis of heated timber elements. Therefore, it is important to test structural timber members under realistic loads. We tested with an eccentric load to induce bending in the CLT, as would be the case in strips of timber walls or columns. Inducing tensile stresses in the first glue line created realistic worst-case conditions with respect to char falloff. The CLT was exposed to a heat flux of 20 or 50 kilowatts per square meter from a gas-fired radiant panel. We used 5-layer CLT. The CLT columns were a bit under 1 meter high and trimmed to 125 millimeters depth, with the first exposed lamella being 20 millimeters thick. The exposed surface was 130 millimeters wide. Glass fiber reinforced polymers, as shown here on the right, were shown to improve the structural performance of load-bearing timber members. This is a close-up of the glass fiber mat attached to the surface. Our proof of concept study, published in 2019, showed the potential of GFRP to improve the fire performance of a timber composite material. Glass fibers are inert and will not oxidize. They can withstand much higher temperatures than timber, although they tend to soften when exposed to temperatures like those commonly expected in fully developed compartment fires. In our study, half of the samples were equipped with a layer of GFRP on the surface. Every bare CLT column experienced char falloff, while the GFRP system was able to prevent all char falloff. Even when the char layer detached from the underlying uncharred timber, the layer of glass fiber mat held the char layer in place and prevented it from falling off. This way, we could compare samples with char falloff and samples without char falloff. Here you can see the increased total loss of cross-section in a sample with char falloff on the left, compared to a sample with glass fiber hindering char falloff on the right. The increased loss of cross-section is the result of an increased loss of char layer. This is primarily caused by falloff of charred lamella. Oxidation of the char layer happened for both sample types, but was less significant for CLT with GFRP. The glass fiber mat hindered oxidation of the char layer. To quantify these visual observations, we measured the residual weight of the columns at the end of the test. CLT columns without char falloff had higher residual weight than CLT columns with char falloff. This indicates lower residual strength for CLT columns with char falloff. This plot shows the temperature evolution at 2 centimeters in depth over time. The heating rate at the location for samples exposed to different heat fluxes is shown next to each curve. The external heat flux clearly influenced the rate of in-depth heating, with faster heating at higher heat fluxes, indicated in orange. Moreover, samples with char falloff, shown in red, experienced higher heating rates than samples with glass fiber, shown in blue. All these results suggest a significant effect of char falloff on the burning of engineered timber buildings, as well as the residual structural capacity of engineered timber structures in a fire. The study highlighted the need for further research on the mechanisms of char falloff and its impact on the in-depth heat transfer and burning of engineered timber, and its consequences for the design of modern buildings made of timber. This brings me to the end of my presentation. I would like to thank my supervisors, Rory Hedden and Dylan Fernando, and the University of Edinburgh and the University of Queensland for their support. My name is Laura Schmidt. Thank you very much for your attention.